Hello guys, and earlier we have seen the torsion and what are the assumptions made for analyzing the torsion, and based upon the torsional bending moment equation, how can we determine the shear stresses and as well as the polar moment of inertia has been involved in that particular component, and what are the theory of torsional equation, how can we take on the assumptions, and these are the major points which has been highlighted in that lecture. Okay, and this lecture which is going to carry about with respect to two different kind of shaft. One is called solid shaft and another one is called hollow shaft. Wherever the solid shaft which has been occurred, that solid shaft has undergone their load barrel equations, that is the solid shaft is pi d power 4 divided by 32, that is what you call the polar moment of inertia. In case if I am going to take about the analysis, if it is a hollow shaft means we need to take pi d power 4 same divided by 32, but instead we are going to add d power 4 minus of d power 4. Okay, so this value which has been nullified by adding their values which has been keep on varying with respect to the polar moment of inertia. Okay, so that has been seen here. Here whenever the given objects, if the j and r is constant, what is mean by j and r means j represents it is the polar moment of inertia, wherever the r represents it is the total radius. Okay, so this polar modulus is equal to j divided by r, and for the circular solid section it takes that polar modulus, it should be like pi into d power cube divided by 16, that is it is the ratio of polar moment of inertia and as well as with respect to the total radius. Okay, so if I am using for the hollow shaft, the same kind of polar modulus formula has been used. One is for that circular section and another one is for the solid section. So both the section which has been using these two different kind of formulas, that is pi into d power 4 minus of d power 4 divided by 16 into diameter. Okay, wherever the d represents it is the external diameter, and it is the external diameter, and as well as small d represents it is the internal diameter. Okay, so accordingly we need to modify the condition to find out what is the actual status. Okay, so this equation we know that well, that is a torsional moment equation. It can be written as an T by J is equal to C theta divided by L. Wherever if I need the angle of rotation, if I want to find out what is the angle, I need to take as per the rules which has been framed by for designing the torsion. Okay, so that is Gj by L is equal to T divided by theta, that is what here it was represented. Okay, and this torsional rigidity is the torque which has been produced as a twist. It may be taken by 1 radian in the shaft per unit length. That is why that tau is equal to total torque divided by polar moment of inertia into the radius of the given shaft. Accordingly, we need to produce their angular deflection and as well as the solid state reactions. Okay, so this is what highlighted here, this one. And the maximum shear stresses occurs on the cross section of the shaft at its utmost over surfaces. Okay, so this can be represented as an tau is equal to g theta divided by L into, that is R. So here the stress variations which has been shown in this circular diagram, here it is starting from 0, and when it is ended, on that ended point we having a maximum amount of stress concentration involved, and in between the values which has been linearly has been increased, which means the value of the stress value has been linearly increased. And in case if I am going to take a cone, or it may be like a cone like appearance, if the object will defend, this object will be helpful to understand their distribution level, stress distribution level along with the cross section. So that is what we need to consider before we going for analysis.